Hey everybody, welcome back. We're going to look at 4 repulsions now, but one of those repulsions, and in a later video, 2 of those repulsions are going to come from a lone pair, and we'll see how that affects the geometry. For example, NH3 is ammonia, so ammonia is the way that things like fish excrete their nitrogen when they're done with it, and it has a particularly unpleasant odor. Now, if we want to go ahead and we want to figure out the geometry of this molecule, we have to start with a Lewis structure. So the Lewis structure is going to look something like this. So we've got 8 electrons, and they are going to be distributed like so. So we have a lone pair here, and we have a bond, and a bond. And to figure out the geometry, we have to count the number of repulsions. So remember, any kind of bond or any lone pair is going to try and stay away from each other as much as possible. So you've got 4 repulsions there, so that gives you that tetrahedral geometry. So let's go ahead and sketch that out. So VSEPR, valence shell electron pair repulsion, says they try and stay far apart, so there's nitrogen in the center. And I know that 4 repulsions will take that tetrahedral shape with that approximate 109.5 degree angle. And the question is here, where do I put the atoms, or where do I put the lone pair? Now, I think it looks tidier to put the atoms on the bottom and the lone pair on the top, but it actually doesn't matter how we do it at all. So this is going to be the approximate geometry of ammonia. And I'm going to go ahead and skip to my PhET website here and just bring this up, and we'll talk through the different kinds of geometries, and we'll talk why the angle is a little bit different than what we might expect to be that of 109.5. So stay tuned. Okay, so here I am in PhET. So I'm going to go ahead and build ammonia. So I've got my nitrogen in the center. I've got 1 bond. I've got 2 bonds. So remember, that's that linear geometry. And as I add a 3rd bond, right, the repulsions move them apart. That trigonal planar. So notice they're all flat. And looking from the top, that's that 120 degree angle. Now in ammonia, we've got a lone pair. So I'm going to click on the lone pair and add it. I'm just going to reorient it so that the lone pair is on the top. And what you can see here, right, is this basically looks just like methane, but you've got a lone pair in place of one of the hydrogens. And if we look at the bond angles, they're approximately 109.5 degrees. We'll see that that's actually a little different. The electron geometry is tetrahedral, so just like before, but if you remember, the molecular geometry is where the atoms are. And if you notice this time here, the atoms are not in exactly the same position as methane because we don't have that hydrogen on top. So instead we have what looks like a pyramid with the purple atom at the top and the 3 white ones at the bottom. And so the name of this geometry is Trigonal Pyramidal. Trigonal because you've got that pyramid shape there, and trigonal because you've got that triangular base. So it's possible to have a square pyramid as well, but this is a triangular pyramid, or trigonal pyramidal. And if I click on real molecules here, I can go ahead and show you what this really looks like. And so I'm going to pull in the top right hand corner ammonia, and so this is what it actually looks like. I'm going to show you the bond angles there. See, they're 107.8 degrees. And so the question is, why are they 107.8 instead of 109.5? And the answer is that that lone pair at the top is kind of big and fat, actually, and it kind of squeezes down and pushes the other angles closer together. And so because it pushes them together, then instead of 109.5, it's about 107.8. So that 2 degree reduction there comes from the fact those lone pairs are kind of large. All right, let's go ahead and draw that out. How would we draw that out on an exam? So we'd start with the Lewis structure, and I've drawn the Lewis structure on one of the previous slides. It would look something like this. Normally on the exam I will say, make sure you carefully start by drawing a Lewis structure. And then we're going to convert this to a geometry. So we've got our 4 repulsions. So we've got that 1, 2, 3, 4, right, that tetrahedral, and sorry, that nitrogen in the center. Doesn't really look like a nitrogen, looks like a W, so let me go ahead and rewrite that. There we go. And then we've got a lone pair, so I've got a lone pair here, and I've got my hydrogens around the base of my pyramid. So this is what the geometry would look like. Some people draw it like so, and I think that's okay too. And some people actually go ahead and they draw that lone pair kind of like, I don't know, it always reminds me of a ghost or something, so kind of something like that. And I think that's equally fine as well. So whichever way you prefer, I would say all of these are valid representations. All these are valid ways to draw the ammonia molecule. And remember, the molecular geometry is where the atoms are. So the molecular geometry is trigonal pyramidal. Okay, so that's the molecular geometry, and some people will just call that the geometry. And the electron pair geometry is tetrahedral. The electrons still have that tetrahedral shape, right? But the atoms are actually only in 3 of the positions here and in the center, so they don't exist in this position here, where if it did, we could call it actually tetrahedral. So those bond angles, again, are on the video, I think I said they were 107.8. So we'll say they're approximately 107 degrees just for kind of fun. So this bond angle here is about 107 degrees, give or take a little bit. And, oh, why is that? So the reason for that, of course, is that they're just so monstrously large, right? So this lone pair on the top kind of squishes back these other bonds here, just like if someone kind of large sits next to you on a bus or an airplane, right? They kind of spill over their seat and they kind of cause you to squeeze back again. So that perfect 109.5 degree angle goes down because this large electron pair, and this is why this is actually kind of a nice way to represent it, kind of squeezes back the other one. So I can kind of draw that in, right, and show that they're kind of squeezing down, and that angle tightens up less than 109.5 degrees, and about 107 degrees is good enough, I would say. You don't have to remember this angle. In fact, on the exam, I would normally only just expect you to know, oh, let me get rid of the lightsaber. I would just expect you to know it's less than 109.5, but if you memorize it, that's totally hunky-dory.